8.3 is on power series solutions to linear differential equations. So let's take a look at this. First, suppose we have this form. This should be familiar. So suppose we have a sub 2 of x, y double prime, plus a sub 1 of x, y prime, a naught of x, y equal to 0. And then standard form standard form, we divide by that leading coefficient that's variable coefficient, right? So form, we have a2 not equal to 0. And we get y double prime, and then they use p of x, y prime, plus q of x, y equal to 0. All right, so we've seen that before, right? That's the standard format we use to make it a little more reasonable. We're going to look at singular points here in a second. Let's do a couple definitions. They call this definition 2. This is what we mean by an ordinary point and a singular point. Okay, so a point x naught is called an ordinary point if both P and Q are analytic at x naught. So are analytic and that means you can express P and Q as a power series, right? About x naught. If x naught is not an ordinary point, it is called singular. It is called a singular point. Of the equation, the given equation of this guy. Well, I guess either of them. Actually, it's the first one. Okay, so let's say that one. Okay, so first let's just look at examples of singular points. And pretty much it's where the denominator is 0. So examples of singular points of equations, differential equations. So suppose you had x squared plus 1 y double prime plus x y prime minus y equal to 0. So essentially when you divide out by the x squared plus 1, that can't be 0. So you're basically looking at x squared plus 1 equal to 0. And you can see that that's only 0 for the imaginary numbers plus or minus I. So plus or minus I are singular. All right. Okay, so next example. Let's list what we had, like x squared y double prime plus 3y prime minus x y equal to 0. And you can see this one's nothing special, really. You can't have that be 0 when you divide it out. So that singular point would be just 0. It's a polynomial. So x equal to 0 is singular. Okay, next example. This one's a little different. X squared minus 1 y double prime plus 1 minus x y prime plus x squared minus 2x plus 1. Maybe you can see where we're going with this. Without dividing, we can see that can't be plus, x can't be plus or minus 1. But in fact, if you divided it out and reduce, you're going to have a removable discontinuity. So a couple things. We're going to do this. We're going to rearrange into that form. And we're going to divide out. So we're going to have y double prime minus x minus 1 y prime over. And then we will factor that to x plus 1, x minus 1. And then we will factor that numerator as well. All over x plus 1, x minus 1. So that's actually a perfect square trinomial, x minus 1, x minus 1. And then we can see that those guys are all gone. So that's what we would refer to as a removable point. So our only singular point, so y equals -1 is singular. And I said y, x equal to -1 and x equal to 1 is removable. Okay. Let's look at another example. Let's look at an example of how to find power series expansion. Not sure we'll have room here, but that's okay. We can go on to the next page. All right, so the directions on this one are find at least the first 4 non-zero terms in a power series expansion about x equal to 0. Okay, so we have z double prime minus x squared z equal to 0. So our p of x is not there, so it's 0. And our q of x is equal to -x squared. All right, so our equation is analytic everywhere. Is analytic everywhere and no singular points. Okay, so nothing to have to worry about there. So basically you let z and calculate z prime and z double prime. Then you have to basically force the power series to be d equals 0 in that form. So what we do is we let, so z is going to be our basic power series. So z is equal to the infinite sum as k goes from 0 to infinity of a sub k x to the k. And then we're going to calculate z prime of x and z double prime of x using our form. So you can look this up again and see how it's calculated. So it goes from 2 to infinity. I'm not going to show you all the little details of this because it would take too long. And then you get this form. One of the things we're going to do is manipulate these indices so they match. So that'll take some work. Oh, wait, I skipped a line there. Sorry about that. We're going to make it look like that in a second. Okay, so then z prime is equal to, so I wanted to, first you start at 1. So 1 to infinity, then we're going to move it later. K a sub k x to the k minus 1. And z double prime, now we'll start at 2. And then you get k minus 1, a sub k, x to the k minus 1, minus 2. So that's z double prime. So go back and double check those, of how you get those. So now we substitute these into our equation. So now we're going to take this z and substitute here, and this z double prime and substitute here. But we need to make our indices match. That's going to be the tougher part. Okay, so now substitute into here. Okay, so I have z double prime minus x squared z equal to the sum as k goes from 2 to infinity, k minus 1, a sub k, x to the k minus 2, minus x squared, sum k goes from 0 to infinity, a sub k, x to the k. Okay, so now we want to shift it. We'll now shift the index. So we want to shift the index so they match, and then you'll have to factor out some stuff. So let's see. Let's see. So what you get hold on one second. All right, so you end up having z double prime minus x squared z. All right, so then you have 0 to infinity. But then if we evaluate at k equals 1 and k equals 2, then you get n plus 2 times n plus 1, a sub n plus 2, x to the n, minus, and then if we start at 2 to infinity, you get a sub n minus 2, x to the n. So now what I want to do is shift this one to 2. So if I do that, that's equal to, then I take out the 2a2 plus 6a3, just doing that calculation. Now this is shifted to the 2, so n is equal to 2 infinity, n plus 2, n plus 1, and I do presume you're going to need to verify all this stuff because it's not obvious. And then minus, and then now the indices will match. 2 to infinity, a sub n minus 2, x to the n. So now we can write that as one power series. So now we can write as one power series and have this equal to 2a2 plus 6a3x plus, and then now it's 2 to infinity. And so now we're just rewriting this as the n plus 2, n plus 1, a sub n plus 2 minus, and then see, I'll be able to take out the x to the n. This is a sub n minus 2. And what I have is that I can take out the x to the n. So I'm basically just taking this out and then summing differently. So I'm setting that equal to 0. And that, so the only way this is 0 if all the coefficients are 0. So that's equal to 0 if and only if all coefficients are 0. So thus, we have 2a2 equal to 0. We have to have 6a3 equal to 0. And that whole thing equals 0. And this n plus 2, n plus 1, a sub n plus 2 minus a sub n minus 2 equal to 0 for all n, equal to 2, 3, 4, etc. So now you basically solve for that. We're gonna let n be 2 and then let n be 3, and you basically get a system to solve. So now we're going to say let n equal 2, and so you get 4 times 3, a sub 4 minus a naught equal to 0. Okay, so then you solve for that now. So a sub 4 is equal to a naught over 12. A sub 5 is equal to a1 over 20. Okay, and then we're going to let n equal to 3 next and see what happens. So we get 5 times 4, a5 minus a1 equal to 0. So a5 is equal to a1 over 20. And so now this is kind of, you want to look for that pattern. So therefore we have this pattern. So now we have z of x equal to, the sum as k goes from 0 to infinity, a sub k, x to the k. So it's a naught plus a1x plus 0x squared plus 0x cubed plus a naught over 12 x to the 4th plus a1 over 20 x to the 5th, and then we continue in that pattern. So then what you end up doing is we look for that pattern. We're basically Going to take out our A naughts and take out our A1s. And so we get this pattern of A naught 1 plus x to the 4th over 12 plus A1, and then it's just x plus x to the 5th over 20, and then it goes in that pattern indefinitely. So you gotta, so that's would be our solutions for z. If z is equal to that, you end up getting these will always be 0, and then you zero out that function, the equation. You zero out the equation because that's what we wanted. It's all the way back here. So when we substitute back in, so here it is, that's equal to 0. So as long as this matches for A1 and A2, it's coming from those two. Okay, so you're moving around and manipulating the index to get the right form is part of the issue. So we'll have to look at a few more of those.